Okay, welcome to the first lesson for chapter 2. Today's lesson begins with a warm-up where I want you to define these 4 terms, or these 4 words that are on the board. The first one being term.
Would Rachel Burton come to the office, please? Rachel Burton.
The second one being polynomial, the third coefficient, and the fourth constant. So I want you to go pause the video and see if you can find some definitions for these. Now, just as a warning, the word term is tricky because it means a lot of things. For instance, in your glossary in your textbook, it means something else. I want to know what the word term means in an algebraic sense. So pause the video and go take a look. Okay, so hopefully you've taken a look and you've looked up those definitions. A term in an algebraic sense is a variable with a coefficient, or it could have also an exponent, or it might not have a coefficient and it might not have an exponent. Or instead of a variable, it could be a constant. And we're of course going to define coefficient and constant later on. But when I take a look at a term could be something like negative 3x squared. So this is an example. So here I have a variable and it has a coefficient and a constant. That's okay. Or another example could be just the number 5. That is a term. Or another example could be x to the power of 3. That would be a term. Or I could just have a coefficient and a variable, so something like 2x. Okay? So all of those are examples of terms. The next word I asked you to define was polynomial. So a polynomial is an algebraic expression that we form by adding or subtracting terms. So I can put together any of the terms that I had above or any other terms by adding them or subtracting them. So for instance, I could take the first and the second term that I had above and add them together. That would be a polynomial. Or I could take my next 2 and subtract them. And I could add or subtract more to that. So I could also have a constant on the end of that, and that would be a polynomial as well. So you guys took a look at polynomials last year when you looked at what our first one here, my first example, is a binomial, and my second example here is a trinomial. And I could have more or less terms in that as well. The next term I asked you to define is coefficient. And a coefficient is the number by which a variable is being multiplied. So for example, in my first term, in negative 3x squared, the coefficient is negative 3. So it's just the multiplier in front. If I was looking at this term up here, the coefficient, the number in front being multiplied, is just a 1. So there's nothing there, but there is a 1, of course, being multiplied by that. In this last term that I had up as an example, my coefficient is 2. So the coefficient is the number in front. If the coefficient is negative, I need to remember that as well. My last word that we were going to define was constant. So a constant is a term with no variables. It's a value that does not change. So I don't care, nothing is varying or variable about it. So my example above, my second term example of 5, that's an example of a constant. Or another example of a constant would be like negative 8 or 3/2. So basically it's just a number, right? Just a number, no variables. So there's 3 examples of constants. All right, so we'll get started on today's lesson, and I hope that you find this just a refresh from previous years. This is nothing really new here. We're going to talk about adding and subtracting polynomials. So our first example asks us to simplify. So it's just jogging your memory. Do you remember what it means when I have adding or subtracting between different polynomials? So the first thing that I need to do to get rid of the brackets is to distribute the sign in front of the bracket throughout all of its terms. So here I'm adding all of these terms in the second bracket. So I'm just going to rewrite the first polynomial without the brackets. And then I'm going to add everything in the second bracket. So I'm adding x squared, and I'm adding negative 9. Now adding a negative is just the same as subtracting, so I can just write subtract 9. And then for my last bracket, I actually have to subtract everything in the bracket. And this is the tricky one. This is the one when we're going too fast, we miss it. So I'm going to subtract 4x squared. And then I'm going to subtract positive 2x. So it's actually subtract 2x. And then finally, I'm going to subtract negative 3. Subtracting a negative is the same as adding. And now I collect my like terms. So you might remember this. Hopefully this is just a refresher. Like terms are all the ones with the same variable and same exponent. So I put the 2x squared together with all the other x squared terms. So I see a positive x squared here and a negative x squared here. When I add those together, I've got like a 2 in front, a 1 in front, and a negative 4 in front. So I end up with negative x squared. You can take a step if you want and rewrite those all beside each other, but you don't need to at this stage. Our second set of like terms are the x terms. So I have negative 7x. Take a look. I am taking the negative with the 7 and negative 2x. So I'm going to put those two together and I get negative 9x. And then finally, my last set of like terms are the constants. So I've got positive 6, negative 9, and positive 3. And when I put those together, I get 0. So I could put plus 0 on the end of my expression, or I could just leave it like it is. Moving on to the next part of our note, we're going to talk about equivalent expressions and functions. So what I want to do is be able to simplify so that I end up with the same expression or the same function. That's what it means for something to be equivalent. It means that they are the same. So simplifying to the same expression would be my algebraic approach. If I wanted to take a graphing approach, I'd have to show that they make the same graph to show that they are, in fact, equivalent functions. So we'll take a look at an example here. My example asks, is this first expression, and the first expression does start here at negative 2b plus 3a, and then subtracting that second bracket. I want to know, is that expression and this expression, are those two expressions equivalent? So what I need to do is either try to graph both of those and show that they make the same graph, or I need to change both of them algebraically until they look the same. So I'm going to use that second approach here. And so for my green one here, I am going to say that this is equal to, and I can distribute that negative sign in front of the second bracket throughout that second term. So I'm just simplifying by getting rid of the brackets. The first bracket stays the same, and then subtracting negative 3a, I get positive 3a, and subtracting positive 2b is subtracting 2b. And then again, I'm going to collect my like terms. So I put the a's together first. We usually put these in algebraic order. So 3a plus 3a is 6a. And then I'm going to collect the b terms. Negative 2b, take away another 2b, would be negative 4b. So that's the first expression that I have. Over here, my second expression, again, I'm going to simplify that by getting rid of the brackets. So I just drop the brackets from the first expression. And then I'm going to subtract everything in the second bracket. So I'm subtracting 8b and subtracting positive 4a. And then I'm going to collect the like terms. So I'm putting the a terms together first. I've got 10 a's, take away 4 a's, that's just 6a. And then I've got 4 b's, take away 8 b's, that's negative 4b. And what I've done here is shown that both of these expressions both simplified to 6a minus 4b. So therefore, the two expressions were in fact equivalent. Moving on to our next example, I want to know if these two functions here, I've named one of them f at x and the second one g at x. I want to know if they are equivalent functions. So this time I'm just going to pause for a second before I try to do any algebra, and I'm just going to imagine what those graphs look like. So there's a couple of things that you could be thinking about here. I could be thinking about the stretch factor on my parabolas. I might be thinking about the direction that they open. And I might be thinking about the y-intercept. So if you were thinking about those things, I hope that you've convinced yourself that these graphs are not the same. So I can see here, if I was looking at the stretch factor, that here I'm going to have a positive 5 stretch factor or a value. And here I have a positive 3 stretch factor or a value. So that's definitely not going to give me the same graph. They both open up, but different stretching. And then I can take a look for my y-intercept. Now remember, if I'm intersecting the y-axis, that means that the x value of that point has to be 0. If I subbed in zeros for all the x's, I would just be left with -4, and that would be my y-intercept in the first function. Or I'd just be left with -11. That would be my y-intercept in the second function. So thinking about what those graphs look like, I'm convinced that those are not in fact equal. So I'm going to prove that they're not equivalent. Now all I have to do here is prove that there's a point that they don't cross. So I'm just going to pick one x value and prove that they have two different y values, the two graphs, and then that's all I have to do to prove that they're not in fact the same graph. So in my example, I said you could use x equals 2. You don't have to. It can pick any number. So for instance, if I picked x equals 1, because 1 is easy to do some math with, I'll just sub 1 into f at x. So I get 13 times 1 minus 4 plus 5 times 1 squared. So I'm just replacing all the x's with 1's. And then I'll simplify this. And I can see that on the first graph, if I went over to x equals 1, the point would be up at 14. So on the second graph, I'll do the same thing. I'm going to plug in the same x value and prove that they don't actually cross at that point. They need to cross everywhere to be the same function. So I'm going into the g function and I'm replacing all the x's with 1's. And then I'm going to simplify this. And I end up seeing that on this graph, when I go over to 1, I go down to -14. This tells me that f at 1, the y value in x equals 1, is not equal to g at 1. So the y value when x equals 1 on the second graph. So because the y values are not the same, these two functions are not equivalent. I've shown that the graphs will not be the same. All right, at this point, what I would like you to do is to take a look in your textbook at page 89, question number 13. And if you're not at home, if you're at school, I'd like you just to discuss that question with your partner.